In this video, we are going to talk about L'Hopital's rule. So L'Hopital's rule is a way of computing limits that we might have otherwise not been able to compute. And so we're going to first talk about some limits that we were able to compute using various techniques. And L'Hopital's rule is a way to just do it in a more general setting. So as you might recall, we've talked about computing the limit as x goes to 1 of x squared minus x over x squared minus 1. And we use algebra for this, where we factored the top and the bottom. So the top factors is x times x minus 1. And the bottom is x minus 1 times x plus 1. We canceled the x minus 1 to get the limit. So x goes to 1 of x over x plus 1. Then we just plugged 1 in to get the limit was 1/2. We also computed the limit as x goes to 0 of sine of x over x. And we found that this was 1 using geometry. And I'm not going to go through the whole argument again. But notice that these both have the property that if we just look at the top and the bottom separately, they go to 0. Meaning, in the first one, the limit as x goes to 1 of x squared minus x is 0. And the limit as x goes to 1 of x squared minus 1 equals 0. So both the top and the bottom in this first expression are going to 0. And the same thing is true for sine of x and x. So what L'Hopital's rule does is it figures out a general way of computing such limits. And this allows us to compute more complicated things that we would not have been able to find the limit of otherwise. And so we have the following theorem, which is L'Hopital's rule. And so it says, suppose f and g are differentiable and g prime of x is not 0 on an open interval that contains a, except possibly at a. Suppose that the limit as x goes to a of f of x equals 0, and the limit as x approaches a of g of x equals 0, or the limit as x approaches a of f of x equals plus or minus infinity, and the limit as x goes to a of g of x equals plus or minus infinity. Then the limit as x approaches a of f of x divided by g of x equals the limit as x approaches a of f prime of x divided by g prime of x, provided the limit on the right exists. Okay, and so with L'Hopital's rule, there are two pieces to it. The first piece is what I was talking about a second ago. So if we have a limit of f of x divided by g of x, where we know both the top and the bottom are going to 0, then that limit is equal to the limit of f prime divided by g prime. Now we do have this one caveat that g prime of x cannot be 0 on an open interval that contains a except possibly at a. Basically this means that g prime of x can't be 0 for like a really long period of time. And so it might be 0 at that value a. In fact, if it is, that's totally fine. But the issue that we run into is if like the derivative is like always 0 or like 0 for a really long period of time or things like that. It's not a big concern. That doesn't happen very often, so we're not going to dwell too much on it. There's also this case of when we have infinity. So if we have positive infinity or negative infinity on the top and on the bottom in the limit, then L'Hopital's rule also applies. And so this will let us compute limits such as the limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. We already know how to compute this, and this was just 1/2, using a shortcut we've talked about before of just comparing the leading coefficients. But L'Hopital's rule also can compute this limit, because it's an infinity over infinity looking expression. And so L'Hopital's rule is a very powerful tool for computing limits. And so we're going to look at some examples of actually making use of L'Hopital's rule. So the first one we're going to look at is a limit that we would not have been able to compute without L'Hopital's rule. So we want to find the limit as x approaches 1 of the limit ln of x divided by x minus 1. Okay, so before you use L'Hopital's rule, you should always check the conditions are met. Now, the first condition of f and g being differentiable, you're going to take the derivatives to use L'Hopital's rule, so if they're not differentiable, you're going to have an issue, because you can't take the derivative. And so that one's fairly straightforward. The bigger one to check is you actually are getting 0 over 0 or infinity over infinity. So if we take the limit as x goes to 1 of just ln of x, this is just ln of 1, because ln is continuous, and that is 0. And then the limit as x approaches 1 of x minus 1. Plugging in 1, you get 1 minus 1, which is 0. So this is, in fact, a situation in which the top and the bottom are both going to 0. And so L'Hopital's rule does apply on this limit. So we have the limit as x goes to 1 of ln of x divided by x minus 1. Then when you use L'Hopital's rule. Now, I suggest always making some indication that you're using L'Hopital's rule, just to make it clear, because otherwise you can get kind of weird expressions, because you are going to take the derivative of the top and the bottom separately, and it's easy to forget what you actually did if you don't use something to denote L'Hopital's rule. So I tend to write L prime H over the equal sign, just to remind me I'm using L'Hopital's rule at that step. Now L'Hopital's rule says I take the derivative of the top and the bottom separately. So the derivative of ln of x is 1 over x. So I get 1 over x on the top. And the derivative of x minus 1 is just 1. And so this whole thing is just the limit as x goes to 1 of 1 over x. And we know what that is. That's just 1. And so we were able to compute the limit of ln of x over x minus 1 is equal to 1. So we were able to compute that limit just using L'Hopital's rule. And this is something we would not have been able to do otherwise, because algebraic manipulation isn't going to really help us too much when natural log is showing up. And so this allowed us to get around an issue that we otherwise may have not been able to solve. So next, let's look at another example. So now we want to take the limit as x goes to infinity of e to the x over x squared. Okay, so looking at the top is going to be going to infinity as e to the a really large number is really large, and x squared is going to get really large as x gets really large. So this is an infinity over infinity looking expression. I'm just going to write in parentheses that it becomes something like infinity over infinity. So L'Hopital's rule does apply here. Now, the sign on the infinity is not relevant. Whether it's positive or negative infinity, that's not relevant in L'Hopital's rule. Both of them are totally fine. If you have like a positive infinity over a negative infinity, all that tells you is that we kind of expect to get a negative answer in the end. Okay, so the signs aren't really relevant for if you can use L'Hopital's rule or not. So we're going to use L'Hopital's rule here. The derivative of e to the x is e to the x, and the derivative of x squared is 2x. So I've got e to the x over 2x. Now notice that the top is still going to infinity, e to the x still goes to infinity, and as x goes to infinity, 2 times x also goes to infinity. So this still looks like infinity over infinity. But that's okay, Because L'Hopital's rule never said that we couldn't do it repeatedly. It just says that the limits are equal. And so, remember, it just says that these two limits will equal. And so if I take the derivative again, which I can do because it's still an infinity over infinity looking limit, then it's just going to be equal to this middle thing, which then is equal to the first thing. And so I'm going to use L'Hopital's rule a second time. And it's just giving us a chain of equalities is all it's doing. So the derivative of e to the x is e to the x, the derivative of 2x is 2, and now the top is going to infinity and the bottom is going to 2. So we get infinity. Now, one thing to note is I did say L'Hopital's rule requires that this limit at the end does exist. And in the past we've said that when it goes to infinity or negative infinity, it does not exist. L'Hopital's rule is fine to take infinity and negative infinity. And so like this does not exist condition in L'Hopital's rule is literally like when we get a limit that does not exist, like doesn't go to infinity or negative infinity. The things that are like wild oscillations or where the left-hand and right-hand limits don't agree, things like that. And so it's totally fine to get infinity or negative infinity in at the end, and that's still the answer. And so the limit, as x goes to infinity of e to the x over x squared, is infinity. Okay, so we have computed that limit successfully now. Now, before we do some more examples, just a few quick notes to make. The first is with regards to what we just mentioned. So first, as long as the conditions of L'Hopital's rule are met, you can repeatedly use it. Okay, so just like we saw in the previous example where I used L'Hopital's rule twice, as long as we keep meeting all of the conditions, so both the top and the bottom are differentiable, the bottom has a derivative that's non-zero on some open interval, which again, the only way that wouldn't happen is if the bottom became like the zero function in the derivative or something like that. And so it's not really a big issue. And then you have to have 0 over 0 or infinity over infinity. As long as those conditions are met, you can keep using L'Hopital's rule. The next thing to note is that L'Hopital's rule applies to one-sided limits. And I guess I should say and limits at infinity. We just did an example of that. But it applies for one-sided limits or limits as you go to infinity or negative infinity. And so that is something to be aware of. And then the last note I want to make is that in L'Hopital's rule, we take the derivative of the top and bottom separately. Now, we just did two examples of that, so hopefully that makes sense. But one thing to note here is we're not using the quotient rule, unless you have to use the quotient rule to take the derivative of one of the pieces. Okay, that is an easy place to make a mistake with L'Hopital's rule. In trying to use L'Hopital's rule with the quotient rule to take the derivative rather than doing them piece by piece. So you do need to be careful about that. Okay, so now we're going to look at a couple more examples of using L'Hopital's rule. So the next example we want to look at is the limit as x goes to infinity of ln of x divided by x to the fifth. The first thing to check here is to check that we actually are going to infinity. So the top is ln of x. As x goes to infinity, ln of x does go to infinity. It goes there very slowly, but it does go there. So it goes to infinity, and x to the fifth obviously goes to infinity. So this is an infinity over infinity form, and so we can use L'Hopital's rule. So taking the limit as x goes to infinity of our expression, we have by L'Hopital's rule, the limit as x goes to infinity, the derivative of ln of x is 1 over x, and the derivative of x to the fifth is 5x to the fourth. And so we have this expression now, which this simplifies as the limit as x goes to infinity of 1 over 5x to the fifth. And at this point, we have 1 on the top, and the bottom is still going to infinity, so we're getting 0. So we get 0 in this limit. Now, the key thing to note here is that we simplified rather than trying to use L'Hopital's rule again. If you try to use L'Hopital's rule again, you get something a little odd here. The top is going to go towards 0, because 1 over x goes to 0, and the bottom is going to go to infinity, which still does suggest that the limit goes to 0. However, by simplifying, we were able to make the limit somewhat easier to deal with. You should always try to simplify after you use L'Hopital's rule before using it again if you can, because that simplification will make the derivatives that you take next easier to work with. And so simplification is just a really useful fact to make use of in L'Hopital's rule. So now let's look at one more example of using L'Hopital's rule. So we want to find the limit as x goes to 0 of tangent of x minus x divided by x to the third. Okay, so we want to compute this limit. So the first thing to do is figure out what the top and the bottom are doing. So let's check that. The limit as x goes to 0 of tangent of x minus x. Well, tangent of x as we go to 0 is going to go to 0, because sine of 0 is 0 and cosine of 0 is 1. So we get 0 minus 0, so we get 0 on the top. And then if you take the limit as x goes to 0 of x cubed, you clearly get 0. So L'Hopital's rule does apply here. And so we're going to make use of L'Hopital's rule. So we have the limit as x goes to 0 of tangent of x minus x over x cubed. Now applying L'Hopital's rule, we have the limit as x goes to 0 of the derivative of tangent is secant squared, so we get secant squared of x minus 1 divided by 3x squared. Okay, so that is our derivatives. Now, in this expression, one thing to note is that secant squared as x goes to 0, that is 1 over cosine. Cosine goes to 1, so secant squared goes to 1. So the top is going to be going to 1 minus 1, which is 0, and the bottom still goes to 0. So this is a 0 over 0 form. So we can use L'Hopital's rule a second time. So making use of the L'Hopital's rule again. We have the derivative of secant squared, so we have to use the chain rule. So we have 2 times secant of x times the derivative of secant of x. So we're using the chain rule on secant squared. The derivative of 1 is 0, so we just have this. Then the derivative of 3x squared is 6x. And this becomes the limit as x goes to 0 of 2 secant of x. The derivative of secant is secant of x times tangent of x, all divided by 6x. We can cancel our 2 with 2 on the bottom, and so we're left with the limit as x goes to 0 of secant squared of x times tangent of x, all divided by 3x. Now secant squared will go to 1, tangent goes to 0, and 3x goes to 0. So this is still a 0 over 0 form. But rather than just taking the derivative outright, what we can do here is we can use the fact that limit properties are something we know about. And so we can split this up into the limit as x goes to 0 of secant squared times the limit as x goes to 0 of tangent of x divided by 3x. Now the reason why we can do this is because we know that secant squared goes to 1. Now we could have done this before as well. The issue that we'd run into is we would have gotten weird expressions. We would have gotten limits that we couldn't really compute. And so that's why we haven't used this idea before. But here we know how to compute this limit. The limit of secant squared I just said was 1, and we did it earlier. So now we just need to use L'Hopital's rule on this piece to get the overall limit. So we're going to use L'Hopital's rule now on tangent of x over 3x, which again, tangent goes to 0 and 3x goes to 0, so we can use L'Hopital's rule. The derivative of tangent is secant squared. The derivative of 3x is just 3. And secant, we've said before, goes to 1, so this goes to 1 over 3. So this other piece is 1/3. And so the overall limit is 1 times 1/3, which is 1/3. And so what we've then got here is that the limit as x goes to 0 of tangent of x minus x over x cubed is in fact 1/3. And so we have successfully computed that limit. So the next thing we want to talk about is the fact that L'Hopital's rule actually can be used in a broader setting. And so we've looked at both 0 over 0 and infinity over infinity showing up in a limit. But L'Hopital's rule applies to anything that's what is called an indeterminate form. And so I'm not going to give a very strict definition for indeterminate forms. But in a sense, indeterminate forms are values appearing in limits. I should say appearing when we plug points into limits. That can, so they might not, but they can result in any value. Okay, so indeterminate forms, basically you can get a lot of things out of them. If they show up in a limit, we just don't know what's happening, in a sense. But L'Hopital's rule allows us to compute the derivatives when we have an indeterminate form. And so a list of the indeterminate forms that we have is as follows. So the following are our indeterminate forms. Two of them we've already seen, 0 over 0 and infinity over infinity. Both of these, L'Hopital's rule can be applied to directly. The next one is what's called 0 times infinity. And then you also have infinity minus infinity. And so those are 4 of them. We are going to mention the other 3 as well. And so the other 3 are when you have 0 to the 0, infinity to the 0, and 1 to the infinity. And so these 7 are the indeterminate forms. So far, we've talked about how to deal with these 2. So these 2 you apply L'Hopital's rule to. Okay, so 0 over 0 and infinity over infinity, we directly apply L'Hopital's rule to. But as it turns out, we can use tricks for the other ones as well. And so the next 2, 0 times infinity, infinity minus infinity, we're going to talk about in this video. And we're going to talk about the other 3, which all are solved in the same way. in the next video. So I'm just mentioning this to you so you know where to look for how to deal with these. And so we've dealt with the first two, now we're going to deal with the next two. And so we're going to talk about a 0 times infinity form now. So with 0 times infinity forms, the trick is as follows. It's a case where the limit as x goes to a of f of x times g of x has the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is plus or minus infinity. And this could possibly go to any value. It depends on how fast we're approaching 0 and how fast we're approaching infinity. So the way we do this is we just convert f times g. And so the way we deal with this is we're going to rewrite f times g as f divided by 1 over g, or f times g equals g divided by 1 over f. Now the trick here is if f was going to 0, then this first expression will become a 0 over, well, g was going to infinity, so we have 1 over something going to infinity, which gets really small. So it's going to be a 0 over 0 form in the first case. And in the second case, g was going to plus or minus infinity. And 1 over f, well, f was going to 0, so the bottom is now going to plus or minus infinity. And so in the second case, you get an infinity over infinity form. And so we're rewriting it so it's now in one of the two forms that L'Hopital's rule applies to. To determine which of these two you use, you flip whichever one's going to be easier to take the derivative of. So it doesn't matter which one you choose to flip, just pick whichever one makes the work easier. Both of them will work. We're going to do some examples of actually doing this now. But it's just this idea of we're just going to flip one of them, rewriting it as 1 over an expression. So let's look at an example. So we want to evaluate the limit as x goes to 0 from the right of x ln of x. Okay, so we want to compute this limit. First, we need to talk about what things are doing, what things are going on, I mean. So if we take the limit as x goes to 0 from the right of x, well, that clearly goes to 0. And so the limit as x goes to 0 of ln of x. Now, you might not know this one, but if you think about the graph of ln of x, it looks like the following. And notice it clearly has a vertical asymptote as you approach 0 from the right. So we are going to get negative infinity for the limit as x goes to 0 from the right of ln of x. So this is a 0 times infinity form. And the way we're going to deal with it is simply by rewriting the expression. So we're going to rewrite this expression in the limit. So we have x ln of x. We're going to rewrite it as something divided by 1 over the other thing. And the question is, what's easier to take the derivative of? Well, it's easier to take the derivative of 1 over x rather than 1 over ln of x. So that's what we're going to do. We're going to write this as ln of x divided by 1 over x. And so this is the whole flipping. I flipped the first one in this case, so I flipped x to be 1 over x. I could have also written it as x divided by 1 over ln of x, but the derivative of 1 over ln of x is harder to deal with. And so you just flip the one that makes the derivative easier. So now the top is going to negative infinity, and the bottom is going to go to infinity. So this is a L'Hopital's rule problem now. And so we're going to apply L'Hopital's rule. So taking the derivative of the top, the derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. And this then simplifies as ln of x, the limit as x goes to 0, of 1 over x times, well, flipping it back over, it's times negative x squared. So we have the limit as x goes to 0 from the right of negative x, which is 0. And so we got 0 in this limit by simply flipping the one expression. Okay, So now we're going to look at another example. So now we want to find the limit as x goes to infinity of x cubed e to the negative x squared. Well, as x goes to infinity, x cubed is clearly going to go to infinity, and as x goes to infinity, e to the negative x squared, well, the exponent's going to get really, really small. So this is going to become essentially e to the infinity, and so e to the negative infinity, I should say, which is essentially going to 0. So this is going to be a 0 times infinity form. And so once again, we need to flip something. Now, in this case, it's kind of obvious what to flip. E to the negative x squared has a negative exponent on it, and so there's a natural way to flip things. So the natural way to flip things here is when I have the limit as x goes to infinity of x cubed over e to the x squared. Okay, now this is an infinity over infinity form. So using L'Hopital's rule, we have the limit as x goes to infinity. The derivative of x cubed is 3x squared. Then the derivative of e to the x squared, well, we have to use the chain rule. So it's the derivative of the outer function, which is just e to the x squared, times the derivative of the inner function, which is the derivative of x squared. So we have the limit as x goes to infinity of 3x squared divided by e to the x squared times the derivative of x squared is 2x. And so canceling things, this becomes the limit as x goes to infinity of 3x divided by 2e to the x squared. Now, this is still an indeterminate form, so we're going to use L'Hopital's rule once again. And so using L'Hopital's rule a second time, we have the limit as x goes to infinity. The derivative of 3x is 3. The derivative of 2e to the x squared is going to be 4x e to the x squared. So as we now take this limit, the bottom is going to infinity still, and the top goes to 0. So we end up with just 0. And so we were able to compute this limit as well. Now, both of these examples did end up going to 0. That is not always the case. It just happened in these examples. That was what was happening. Okay. So the next one we want to talk about is infinity minus infinity form. And so in this case, if we have the following, if we have the limit as x goes to a of f of x as infinity, and the limit as x goes to a of g of x goes to infinity, then the limit as x goes to a of f of x minus g of x is an infinity minus infinity form. Okay, so this one is a bit different in that you do have to have both pieces going to infinity. So the sign does matter here. If you have like infinity minus negative infinity, that's just infinity plus infinity. That does go to infinity. So the sign does matter here. And so the example for this that we're going to look at is we're going to take the limit as x goes to 1 from the right of 1 over ln of x minus 1 over x minus 1. So just checking that this actually is an infinity minus infinity form, we check that we have the limit as x goes to 1 from the right of 1 over ln of x. Well, ln of x as x goes to 1 from the right goes to 0. So this is going to be like 1 over something really small. So this does go to infinity. Limit as x goes to 1 from the right of 1 over x minus 1. This also goes to infinity. So this is an infinity minus infinity form. And so the way we deal with it is we're going to combine it into one expression. So we're going to get a common denominator and then go from there. And so rewriting this with a common denominator, we're just going to cross multiply. So we're going to multiply the first expression by x minus 1 on the top and the bottom. The second expression by ln of x on the top and the bottom. So doing this, we can combine things. So we have the limit as x goes to 1 from the right of now x minus 1 minus ln of x divided by x minus 1 times ln of x. Okay, and so that is now our new expression. And now we just need to use L'Hopital's rule on this in theory. You have to check, is this actually need L'Hopital's rule? And so let's check what things are doing in this new expression. But this is now a fraction, so it could be a 0 over 0 or infinity over infinity type. We do have to check. So checking the first part, we have x minus 1 minus ln of x. Well, x goes to 1, so we have 1 minus ln of 1 is 0. So the top is going to 0. And then in the bottom, we have x minus 1 times ln of x. X minus 1 goes to 0. Ln of x goes to 1. Also goes to 0. So this is a 0 over 0 form. So you do need to check that. It most likely is 0 over 0 or infinity over infinity. But occasionally things may be cancelled, so it was not that case. But this is a 0 over 0 or infinity over infinity form, so let's use L'Hopital's rule now. So we have x minus 1 minus ln of x divided by x minus 1 times ln of x. So using L'Hopital's rule, the derivative of the top is going to be 1 minus 0 minus 1 over x. And the bottom, we have to use the product rule on. So the derivative of x minus 1 is 1, so we get 1 times ln of x, plus x minus 1 times the derivative of ln of x, which is 1 over x. Okay, so simplifying, this is then the limit as x goes to 1 from the right of 1 minus 1 over x divided by ln of x plus x minus 1 times 1 over x. Simplifying it, I'm going to multiply the top and the bottom by x over x, just to clear the mixed fractions that are showing up. So this is the limit as x goes to 1 from the right of x minus 1 divided by x ln of x plus x minus 1. And so we've now got this expression. The top is still going to 0, and if you plug in 1 in the bottom, you see that you get 1 times 0 plus 1 minus 1. So it's still going to be a 0 over 0 form. So we're going to use L'Hopital's rule once again. So using L'Hopital's rule a second time, we're going to get 1 as the derivative in the top. The derivative of x is 1, so we have 1 times ln of x plus x times the derivative of ln of x, which is 1 over x, plus 1 minus 0. So this is then the limit as x goes to 1 from the right of 1 divided by ln of x plus 1 plus 1. And so we have then the limit as x goes to 1 from the right of 1 over 2 plus ln of x. The top is going to 1, and the bottom is going to 2 plus 0, which is 2. So we get out 1/2. And so we have successfully computed this limit that was an infinity minus infinity form. And now the last example that we want to look at is as follows. So we want to compute the limit now as x goes to infinity of e to the x minus x. This is clearly going to be an infinity minus infinity form. That should be pretty straightforward just from looking at it. So now, when you don't have like a natural way to get common denominators, what we do is we factor something out of everything. So I'm going to just factor x out of everything. That looks a little weird. It's just to make it a product. So we're just making it into a product. So I have x times e to the x over x minus 1. And the way you do this is you just pick one of the functions and basically divide it out of everything. And so I picked x, and so I divided x out of everything. And so now we check, is this still an indeterminate form? Well, x is going to go to infinity. And so the question is, what does e to the x over x minus 1 go to? Well, for the sake of time, we actually have talked about e to the x over x squared. And using L'Hopital's rule on e to the x over x, you can show this does still go to infinity. L'Hopital's rule does apply, and the derivative of e to the x is e to the x. The derivative of x is 1. So that goes to infinity, and then you're subtracting 1 from it. So this actually is infinity times infinity. That's not an indeterminate form, and so this limit just goes to infinity. And so with infinity minus infinity forms, you may actually not really have to use L'Hopital's rule. We still technically had to use L'Hopital's rule on e to the x over x, but we did something very much like that before, which is why I brushed that under the rug. But that's the other type of thing with infinity minus infinity forms. You either get a common denominator, like we did in this example, or you just factor an expression out.